I don't think I did a particularly good job of of explaining this answer to you on the video that I made yesterday. So I'm going to go back over this again and record it, and I'm recording it now so that you can understand it. In number 18, this looks like a really difficult problem. But before, anytime you're in a data table and a problem, you should analyze the data table first. So let's take a look at what's going on in that data table. We have two objects, and according to this data table, object 2 has a specific heat that's 3 times larger than object 1, correct? However, when we look at the masses, we see that object 2 has a mass less than object 1, and in fact, by 1/3, by a factor of 1/3. Isn't 20 1/3 of 60? So that means, let's just say I call 60 y. We say y is equal to 60. That means that 20 is equal to 1/3 y. Right? Everybody agree there? Okay, it's very important that you follow this step by step and understand what everything means. So let me make, oh, now I made it look like a 2, didn't I? What I meant was 1/3. Okay, so the problem says, using the information in the table above, if object 2 takes 4,000 joules to heat at 1 degree, how much heat energy will be needed to raise the temperature of object 1 degree? Okay, now, and when you look at this on the video, I do not believe the marks that I put in here in the data table are going to show, because that's on kind of like a picture and it won't show, but what I have down here underneath the question should show. So let's just write that out here. We're going to be using the equation that the heat is equal to mass times C times change in T. Right? Because it's asking about heat. So let's do what we know for number 1. For number 1, we know that the mass is equal to y, because we said that 60 was equal to y. We know that C is equal to X. That's what the table tells us. And what is the change in temperature? 1 degree, right? Problem tells us 1. For number 2, we know that the heat is 4,000 joules. And we said the mass for number 2 is 1/3 of y. C is 3x, 3 times x. And what is the change in temperature? 1. Right? Okay. So, doing our algebra here, we have just shown that number 1 is going to be y times x times 1, which is just y times x. For number 2, we have 1/3 times y. What is 1/3 times y? Or, excuse me, 1/3 times 3? 1. Isn't 1/3 times 3? 1. So these two cancel each other out, the 1/3 and the 3, and we again come up with y times x. And we were told that y times x, number 2, is equal to 4,000 joules. So how much is 1 equal to? If y times x for number 2 equals 4,000 joules, what is y times x for number 1? 4,000 joules. Okay, the point being is that whenever you have this reciprocal arrangement here, so if let's say my y is 1/50th, and my x is 50 times. The 150 times 50 always cancel out. If it's 1/100th times 100, It always cancels out as long as these two temperatures are exactly the same. As long as the temperature change is the same, if your specific heat is proportional to your mass and is a reciprocal, then they're always going to cancel out. Okay, so the answer to this is 4,000 joules. Okay, number 19. An aluminum block is got a mass of 5 kilograms, and it has a specific heat equal to 900 joules per kilogram K. And right here, they give you a number. It absorbs heat 1,340 joules. When you see that joules, that means that it's Q. So that's equal to 1,340 joules. The unknown is what is the change in temperature. So again, our equation is just the Q is equal to the mass times C times the change in T. Only this time they give us Q. 1340 joules is equal to 5 kilograms times 900 joules per kilogram K times our change in temperature, which is what we're looking for, which just means our answer is 1,340 joules divided by our 5 times 900. And be careful the way you put that in the calculator. Be careful. If you hit 1340, divide, and then put 5 in parentheses and 900 in parentheses, if you do that, your answer will come out wrong. Okay? You have to put everything under the divide sign in one set of parentheses. So your answer there, if you do it correctly, comes out to, I believe, 0.29. Somebody do it? 0.2977 something, so it's 0.298 rounded off. Okay? The next one looks like a very difficult problem, but it isn't. Let's read it. It sounds difficult. It's got all kinds of technical jargon. An ideal gas undergoes an isobaric expansion process. So what is an isobaric expansion process? Another one you can tell your mom and impress her. What does that mean? It's done under constant what? Constant what, guys? Pressure. Thank you. Capital P. So our givens are that we have a gas with a pressure of 310 kilopascals. I know that term doesn't mean much to you, but it really doesn't matter at this point in time. Okay? It has an initial volume, capital V, of 2 cubic meters. It has a final volume of 10 cubic meters. So that means that our change in volume is going to equal V2 minus V1, which equals 10 minus 2, which equals 8. The question is, what is the work done on the gas? Please make sure you have this equation on your card. We didn't do a whole lot with this equation. This one, you remember that little slip of paper that was in your baskets? That was this problem. It is work done on a system is equal to negative pressure times the change in V. So even though this looks like a very, very difficult problem, it isn't. It isn't any more difficult than your momentum problem. You're just going to multiply 310 times your change in velocity, which was 10, and this is going to be negative. Don't forget your negative sign, which gives this negative 2,480. Okay, and that's work, so this is in joules, but it's negative. So this is going to be on a griddable. I have to put my negative sign in that first column, and I have to bubble it. If this is a negative answer, you have to do that. And remember, we talked about the fact that anytime your volume is getting larger, expanding, your work is going to be negative. Anytime your volume is getting smaller, it's going to be positive. But if you set up your math correctly, that negative is going to come up there anyway. You wouldn't even have to worry about it. It is 8. 10 minus 2 equals 8 cubic meters. Oh, I'm sorry. You're right. You're right. You're right. Thank you. This should be 8. I knew the answer came out to... I'm like, how do I get 10 times that? All right. Thank you very much. Everybody watching the video, Sam caught me, all right? All right, so let's go on to the next one. And this is the one, people, that is going to be the hard one. Okay? So in this one, this is just like our experiment we did. They're taking a copper wire. They're going to drop it in some liquid. Notice this liquid is not water. It's got a C sub P of 2100. So in this one, our given is, I'm going to, and what they're asking here for is the equilibrium temperature. What is an equilibrium temperature? What is another word for that? Another 2 words. What is it? Equilibrium temperature is where it is the same temperature. And what else is it? In this problem, what is another name for it? The final temperature. Right? Remember that? Okay. So, I'm going to call copper our mass A. And mass A is equal to 0.2 kilograms. And its specific heat is 385 joules per kilogram K. I forgot my 5, didn't I? 385 joules per kilogram K. And its initial temperature is equal to 80 degrees C, but in this one we cannot use C. We have to change it into Kelvin by adding 273. Our other mass is our liquid water, or liquid that's not water, and it is 0.1 kilograms. Its C is equal to 2100 joules per kilogram K, and its initial temperature is equal to 20 degrees C, which again we have to add 273 to. This makes 293. So, our equation is that big long one. Make sure you have it written down. This is the initial temperature of the metal plus the initial temperature of the liquid all over the mass and specific heat of the metal plus the mass and specific heat of the liquid. And I think you guys can see that now this is where This is where the problem comes in, is making sure that you got all the numbers in the calculator right. So this is going to be 0.2 times 385 times 353. And notice, if I've got it all lined up here, I'm just reading them off. It makes it a whole lot simpler to get it right. And this is 0.1 times 2100 times 293 all over 0.2 times 385 plus 0.1 times 2100. When you get this answer will be in Kelvin. It will not be in degrees centigrade. And isn't that what it asked for? Remember, we had to change our temperature. We had to change our temperature to Kelvin. So our answer is going to come out in Kelvin. And if you put that number in the grid, you're wrong. It doesn't know. It doesn't know that yes. If you do this correct, the answer in Kelvin is 309. Right, and remember it said rounded off to the nearest whole number, so in Kelvin it's 309. You have to subtract 273 to get it back into Celsius, which would make it 36 Celsius. Okay? If you, again, everything under that divide sign has to be in a set of parentheses. If you use parentheses within the parentheses, that's fine. You don't have to. You can say 0.2 and hit the times button. 385 plus 0.1 times 2100. But you had to have that whole thing in parentheses underneath the divide sign. You had to have the top all in parentheses. Because if you didn't do that, whatever this equals right here, the calculator would take that and divide it by just this here. That's the way your calculator would work. If there's any doubt at all, get the answers to each one of these sections, add them together, and then divide. Do it piece by piece by piece. It'd be very upsetting to set that whole thing up, and the only reason why you get it wrong is because of the calculator. That would be very upsetting to both of us. Okay. And last but not least, we have this about thermal expansion. We have two copper rods. One is 5 centimeters, the other is 50 centimeters. They both experience a 30-degree change in temperature. Okay, they want you to compare the change in length. So, in comparing the change in length, remember our equation is change in length is equal to the coefficient times the original length times the change in temperature. Okay? And what this says to us is that the change in length depends on what it was initially, and the change in temperature depends on both of those things. So mathematically speaking, we have one length equal to 5 centimeters. We have another length equal to 50 centimeters. Both of them have the same alpha. Because they're made out of, both of them are made out of copper. And both of them have a change in temperature equal to 30. All right. If I want to know what the change in length of this one is, it would equal 16 times 10 to the negative 6th times 5 centimeters times 30. And if you do that correctly, you're going to get 0.0024 centimeters. This one over here is also going to be equal to 16 times 10 to the negative 6. But this one's going to be times 50 times 30. This will equal 0.024 centimeters. Point being is that the one that was longer in the first place gained more length. And to be perfectly honest with you, you are not going to really have to use this equation. If you needed to use this equation to answer it, you've got it. But if you just know the fact that the longer a substance is in the first place, it's going to gain more length given the same change in temperature. I have a small rod, I have a large rod. The large rod gains more length in the same temperature change. Okay? Alrighty.